5.1 notes are about the slope of a line. And the slope of a line is the steepness of the line. And a more mathematical way to talk about slope is talking about the rise over the run. An even more mathematical way of talking about slope is represented by the variable m, and m equals y minus y over x minus x. That formula, y minus y over x minus x, says the same thing as rise over run. The y minus the y is how much the line is rising, and the x minus x is how far it's going to the right, or how much it's running. Take a minute, pause the video, and draw these two lines, and then we'll work on finding the slope of those two lines together. For the first line, I'm looking for some nice points to use, and there are smiley faces at the nice points. And I want to count between those 2 points, how much do I need to rise and how much do I need to run. In this case, I rise 2 and I run 4. So the slope, the rise over the run, is 2 over 4, or in lowest terms, 1/2. For the second line, I'm not rising between these points, I'm actually going down between the 2 nice points. So I'm going to have a negative slope. I go down 1, 2, 3, 4, 5. And you always run to the right, and we're running 1, 2, 3, 4, 5, 6, 7, 8. So the slope, or the rise over run, is negative 5 over 8, because we're going down 5 over 8. We can also find the slope of a line without a picture, and we're going to use that other formula. Pause the video and write down these 2 examples, and then we'll work on them together. The formula that we're going to use is y minus y over x minus x. Now a more mathematically correct formula would be y2 minus y1 over x2 minus x1. And that just means you're going to take the second y value and subtract the first y value. So the second y value is 2, minus the first y value is also 2, over, then we need to do the second x value minus the first x value. Negative 1 minus 1. When we subtract, we get 0 over negative 2, and it is okay to have a 0 on at the top of a fraction. It just equals 0. You might remember that it's not okay to have a 0 on the bottom, because dividing by 0 is undefined. And it looks like that's what's going to happen in this next example. If we do y minus y, we get 3 minus negative 2 for the top of the fraction. But on the bottom of the fraction, when we do x minus x, we have 1 minus 1. So when we subtract, minusing a negative is actually like adding those 2 numbers together. So we get 5 over 0. And it is not okay to have a 0 on the bottom of the fraction. That is undefined. So the first one had a slope of 0, the second one had a slope that was undefined. And if we look at what the pictures for those would look like, the first one went through the point 1, 2, and the point negative 1, 2. It was a horizontal line. Horizontal lines have 0 slope. The second one went through the point 1, negative 2, and 1, 3. It was a vertical line. Vertical lines have undefined slope. Pause the video and see if you can draw a picture of these 4 situations. Draw a line with a positive slope, draw a different line that has a negative slope, draw a line with 0 slope, and draw a 4th line that has an undefined slope. Pause the video and try that on your own, and then we'll compare answers. Here are answers for you to compare with. A line with positive slope is anything that goes up as you look at it from left to right. So this line has a slope that's positive. The second one has a slope that's negative because as I look at it from left to right, it's going down. 0 slopes are any horizontal line, and undefined slopes are any vertical lines. I remember that by thinking of skiing. If I were skiing on this line, it would be 0 fun. Unless I was cross-country skiing, I guess. And if I were skiing on this line, I would become undefined because I'd fall right off the line. So that's one way I remember which ones are 0 slope and which ones are undefined slope. Here's a word problem involving slope. In 1980, U.S. restaurants sold $120 billion worth of food and drinks. In 1990, they sold $239 billion. And in 2000, they sold $376 billion. Find the rate of change between 1980 and 1990. Sorry about that. Rate of change between 1980 and 1990, and also between 1990 and 2000. Explain the meaning of the rate of change in each case. Pause the video and write down the problem, and then we'll work on solving it together. First, between 1980 and 1990. When we figure out the rate of change, we're going to think of ordered pairs. The first ordered pair is going to be 1980, $120 billion. And since they're all in terms of billions of dollars, I can just say 120. My second ordered pair is 1990, $239 billion. Then I'm going to find the slope, y minus y over x minus x. Y minus y over x minus x. When I subtract, I get 119 over 10, which is 11.9. Now what does that mean? Well, the numbers on the top were in dollars, and they were actually billions of dollars. So this is $11.9 billion. And the numbers on the bottom were in years. So we're changing by $11.9 billion per year. Each year between 1980 and 1990, the U.S. restaurants sold $11.9 billion more of food and drinks. Pause the video and try to repeat this process on your own and find the rate of change between 1990 and 2000. Let's work through how you'd find the rate of change between 1990 and 2000 together. First, you need an ordered pair for each one. The ordered pairs are 1990, $239 million, and the second one is 2000, $376 million. Then you find the slope by doing y minus y over x minus x. Once you actually subtract the numbers, you get 137 over 10, which is 13.7. So the slope is 13.7, which represents $13.7 billion per year. That means the restaurant industry was growing at $11.9 billion per year in the 80s, and then $13.7 billion per year in the 90s. It was growing faster in the 1990s than it was in the 1980s. The last thing in this section is graphing lines that are like x equals 6 or y equals negative 3. Write down those two equations and make yourself a t-chart so that we can make some ordered pairs, and also make yourself a graph for each one of these two equations, and then we'll work on them together. In the first case, on our x and y chart, the x number has to always be 6. The y can be any number we want, so 6, 1 would work, 6, 0 would work, 6, 10 would work, 6, anything, 6, negative 5 would work. So let's plot those on the graph. 6, 1, 6, 0, 6, 10, and 6, negative 5. If I connect all of those points, I see that they all lie in a straight vertical line. Whenever you have an x equals a number equation, that is always going to be a vertical line. Now we have a y equals equation, y equals negative 3. Pretty similar, but this time instead of the x having to stay the same, the y has to stay the same. It's always going to be negative 3. The x could be whatever I want. So if we plot those points on the graph, 0, negative 3, 1, negative 3, negative 5, negative 3, and 7, negative 3, we notice that those points all lie in a straight horizontal line. In fact, anytime you have a y equals a number equation, it is always going to be a horizontal line. You might also have a line that's sort of in disguise. 3x equals negative 6 is a line that's just like those but kind of in disguise. This is an x equals equation. It just has a 3 in front. And if I want to undo that multiply by 3, I need to divide both sides by 3. So this is the same as a graph of x equals negative 2. If I remember whether that's horizontal or vertical, I can just make the graph. If I've forgotten, I can make a table of values that have an x value that's always negative 2 and a y value of whatever I want. If I graph those, I'll be reminded that x equals lines are always vertical lines. The homework for section 5.1 is in your packet. It's a 5.1 worksheet.